Okay, I think we can start now. We can begin our webinar. If other persons will join this webinar, they will do it during the presentation. So once again, good afternoon. I'm Enzo Martinelli from the University of Salerno. I'm going to give you this seminar about the RC strengthening of the strengthening of RC beams by FRP externally glued to them, with particular focus on the flexural strengthening in bending. Although I'm from Salerno, I'm currently in Lyon, so I thank you, Emmanuel Ferrier, for organizing this cycle of seminars or webinars, and also for hosting me during for this seminar. So we can start with our presentation. This is the overall plan of webinars which are scheduled for the coming weeks and months. We are now on the second seminar, actually. Whose title is specifically RC beam strengthened for flexure. This is just a short picture to say where I come from, Salerno, which is in the south of Italy, and then we can start with the topic of this seminar. And this is more or less the overview of the outline of my presentation. We will start with talking about materials. I will give you just the minimal information about FRP systems, because the first webinar given just by Emmanuel Ferrier was, covered just the description of FRP systems. Then I will go in details about the interaction between FRP and the concrete members, and particularly I will talk about the observed and the typical failure modes observed in FRP strengthened RC beams. And of course, I will give you informations and some mechanical insights about the bond, which is the key mechanism governing the behavior of FRP, the interaction of FRP and concrete. And then I will show you also a worked example, a realistic worked example, as you will see at the end of my presentation. And I will close my presentation with some alternative solutions with respect to the classical FRP bonded to concrete. I will show you some more modern, more recent solutions like mechanically fastened FRP or pre-stressed FRP and something like that. You will see few slides at the end of my presentation. So let's start with the FRP. As you all know, FRP are materials made of two main phases, the fibers and the matrix. And of course, there is an interface between matrix and fibers, which is often a critical point, which often controls the behavior and the resulting mechanical properties of composite materials. We are not interested so much in describing the behavior of FRP materials as such, but because we are mainly interested in studying how these materials, these systems interacts with concrete. This is the purpose of this presentation. Here you see some pictures from possible materials, from fibers, with several arrangements, from unidirectional to bidirectional, multidirectional, some bars and other fiber. This is on the left of your slide, and then on the right you see the typical B-component epoxy matrix, which is used to assemble to prepare the composite system. Here you see an overview of the materials, usually constituting the fibers. They are the most common ones are carbon classed aramid, and these are the materials actually covered by the current guidelines, the guidelines currently available worldwide, and these are specifically the materials which will be covered also in this presentation. But more recently, other possible materials such as basalt or natural materials like jute, sisal, and other natural materials are used as fibers, and also this is a very recent evolution of composite materials. There are also metallic, especially steel-based composite materials. So these are the materials which are actually available, even though this presentation will mainly focus on the first three ones, the ones boxed in this red rectangle on your left. Just a few words to remind you something which is nowadays known about the advantage of using FRP systems in lieu or other more traditional materials in civil engineering, like steel, for instance. FRP are characterized by lightweight, by high strength, especially by high specific strength, which means by a high ratio between the strength and the weight itself. FRP are corrosion-free with respect. This is a key advantage with respect to steel-based materials, and this is advantage for durability-related issues. And also these three properties, lightweight, strength, corrosion-free, may make FRP a very versatile material which can be used in several applications for strengthening both concrete and masonry members, existing members. Observed failure modes. Now we start examining how FRP interacts with concrete members, with beams, especially. Today we talk about Flexural, so our members are mainly beams. So you can see here some pictures which reminds you, which summarize the main observed failure mode. Observed because they were observed in experimental tests and also in field applications. There are some failure modes, especially this one, this crushing of concrete, which is not new. This is the classical failure mode for RC structures. Usually when you talk about ultimate limit state of RC members, you usually consider this failure mode, the fact that concrete crashes, or in other words, the fact that concrete attain a certain ultimate axial strain. So this is not new for our material. This is something which is a classical failure mode of concrete members, reinforced concrete members. Other new failure modes are those which have to do with the rupture of FRP. Like in this case, you can potentially have a rupture, a tearing rupture of FRP. This is not common, but theoretically it can happen if the FRP section is not too big, it's not too large. So theoretically there is another material. So there is another material which can develop an axial rupture. And you see here on the right a stress-strain diagram, which on the one hand highlights the fact that these materials, especially carbon, but also glass and also aramid, these are the three curves, fiber reinforced, are usually characterized by a quasi-elastic and elastic brittle behavior with respect to the elastic plastic behavior which is characteristic of steel. So on one hand you have a material which can be even significantly stronger than steel, but can be also rather more brittle. And so this is this is the first failure mode which is peculiar for this FRP strengthened systems. But as I told you, the fact that FRP rupture actually occurs is not really a common failure mode in FRP strengthened members, RC members, because the loss of bonding is generally the most common failure mode. This loss of bond can either happen at the end, here, close to the cutoff section, the section in which the external plate ends up here. It can either develop just beneath the adhesive layer or more internally across the concrete cover, but this is mobilized by the same kind of stresses. Actually, the difference is a little bit different in these two cases, but actually the mechanical reasons for this mechanism to develop are almost the same. And there is even an even more typical failure mode, which is this intermediate crack-induced interfacial bonding, which is really a peculiar failure mode for FRP strengthened RC beams. And a significant part of my presentation will be devoted to try to give a mechanical interpretation, a mechanical explanation of this failure mode, which is really a critical one. Failure mode developing from internal cracks and then, beginning from internal cracks and then developing throughout the interface up to the end. So these are the new failure modes we have to face with respect when we consider FRP strengthened RC beams. So these are the new facts which we have to take into account. Today we talk about flexural strengthening. So this shear failure is not actually covered in my presentation today. This will be specifically addressed by the next seminar, which will be dedicated to the shear strengthening of members. So basically we are going to spend half an hour or some time to discuss about the plate end separation, this kind of the bonding which occurs in this zone, in the neighborhood of the cutoff section, and this intermediate bonding failure, which develops more internally across the bending-induced cracks. There are other failure modes which are due to defect or which are due to shear cracks, which will not be explicitly covered in this presentation because the defects usually are covered by safety factors, and as I said, the shear strengthening is not part of this presentation. So bond between concrete. As you see, these new failure modes are generally controlled by the bond which develops between the FRP strip glued to concrete and concrete itself. So we have to investigate and we have to understand how bond works. These are the repetition of the previous slide to say that we are starting to discuss about the plate end separation. So the first, the following slide will be mainly addressed to understand which are the mechanical drivers, the mechanical motivation for this plate end interfacial bonding, the debonding. Let's try to introduce some models, because of course there is an empirical understanding of the phenomenon, but we need, as engineers, we need to introduce models which allows us to have a more in-depth understanding of the mechanical behavior of structures we are under consideration. So let's suppose to develop a first model, very simple one, based on these three assumptions, on these three hypotheses. Let's suppose that all materials are linear elastic. Let's suppose that there is full interaction, so there is no relative displacement between the FRP and the RC beam, which is not clearly the case, but this is just a first first simplified model. So full interaction, no relative displacement, no interfacial slips between the FRP strip and the RC beam. And then let's suppose, just to start understanding what's going on these systems, that we have all uncracked sections, which is also the case because we are talking about the end part in which bending moment are low, so it's not unrealistic to talk about to consider uncracked section. So if we have linear elasticity, full interaction, which means basically that plane sections remain plane as usual in beams, and we have an uncracked section, basically we can evaluate the interfacial shear stress between at this interface between the FRP strip and the RC section by means of a very well-known model, which is the Jurafsky formula. So, as you know, the Jurafsky formula provides you with the interfacial, the mean average interfacial stress as a function of the shear force, the centroidal moment of inertia, the static moment of the part of the section which is below or beneath the interface. So I am in this interface, so I have the AF, BF, which are the dimension of this part of the section. So this is the static moment of this plate with respect to the centroid of the composite section. So what is important is that if you work out this relationship, you can easily realize that Tj can be expressed by means of this EA star, which is an equivalent axial stiffness of the members, taking into account both the axial stiffness of the RC beam and the axial stiffness of the FRP, and also D, which is the theoretical distance between the centroid of the strip and the centroid of the RC beam. But what is important, what I would like to emphasize, that as you all know, tau, in the case of FRP strip running up to the theoretical support, tau, the interfacial shear stress, is similar to the shear force diagram. So we have a stepwise diagram. Here we have a finite value, which can be theoretically evaluated by means of this equation. And then we have a sharp discontinuity across the point in which the force is applied, and then you have zero shear force and zero interface bond stress. This is the case of these three of a model based on these three assumptions. But as we said, full interaction is not a realistic assumption. We have, as you will see here, we have a layer between FRP and the RC beam. We have a layer made of an adhesive, typically made of an epoxy resin. So we have a flexible layer which is characterized by means of a certain elastic properties, and especially by means of a shear modulus. GA is the shear modulus of this layer. So I can easily realize a possible relationship between the interfacial slip, the interfacial relative displacement S, and mobilized shear stresses tau, which depends on this shear modulus KL, which in principle is the ratio between GA, the shear modulus of this layer, and its nominal thickness. But experimentally and also numerical evaluations have highlighted that since the adhesive layer has a modulo of elasticity which is in the same order of magnitude of concrete, there is a certain interaction between adhesive and concrete, and also a part of this concrete takes part in the deformation. So TA is not this nominal thickness of the layer should be replaced by an equivalent thickness of this layer, which depends actually on the ratio between the shear stiffness of the adhesive and the shear stiffness of concrete. If we add an adhesive layer which is very flexible, we will have that T effective would reduce on TA, but T effective is as higher as the shear layer, the adhesive layer is stiff. Usually, if you look at the literature, you'll find that you'll find suggestions of for evaluating TA effective by means of by considering 20 or 30 millimeters of concrete. So T effective is the nominal value of the adhesive plus a certain thickness of the concrete. But this is not. This is just a detailed. This is just a detail in our presentation. What it is important is that there is a flexible layer between our FRP and our concrete, which means that plane section cannot remain plane. When you have this kind of kinematics, you can approach, you can study you are in partial interaction because there is this adhesive layer, and for this situation you have the Newmark theory, which is maybe it's not so common as the Juraski one, but those of you who are familiar with B-layer composite sections, especially with the steel concrete composite systems, are probably familiar with the Newmark theory, which is it's not complicated, but it is based on some differential equation, which here, for the sake of simplicity, are omitted. But you can imagine that the solution you get by applying the Newmark theory in the case of partial interaction is very close to the Juraski one, but it's not a stepwise solution. You have a gradual transition between non-zero tau up to the zero tau, and this transition is as gradual as the interface is flexible. So if you have a flexible interface, you have a more gradual transition. If you have a very stiff interface, you have basically your solution reduces to the former one. So you have this intersection, this more regular transition between the part in which the shear force is non-zero and this part in which the shear force is actually zero. So we have now a model of a more realistic situation. Two materials glued to each other, so with some interaction, some partial interaction, some displacements developing at the interface. So we have this distribution, but our systems, our FRP strengthened beams are not generally strengthened up to the theoretical support, because this is not technically possible, because here, for instance, you have a column, or you cannot access this position. Usually, FRP is interrupted somewhere at a certain distance, A, say, from the point. What is the consequence of this distance between the cutoff section and the theoretical support? Well, you have a system. We are assuming that the system is linear so far, at least so far. So we can apply the superposition of you can consider the superposition of effects. So we can see that this system is indeed equivalent to a system like this, in which we apply a force Fa, which would have been the same force developed in the case of a continuum strengthening, like in this case. So if you have here, you have a almost constant tau. So Fa is the integral of this tau. So basically it's tau times Bf times A. No? So Fa is applied here, and then there is another system which is with an opposite Fa. So if you add this system to this other system, this is equal to this one, and the effects are also can be also superimposed, because we are in linear elasticity. So for this solution, for this system, which is basically equivalent to a continuous, to a complete strengthening, we have already studied the solution, which can either be generated by means of the Jurasky solution, or the more accurate Newark one. And for this system, this system basically resembles the pull-out, the situation of a pull-out of a FRP joint like this. So a glued FRP strip under a force applied here. So the same situation of a pull-out test. So now, since we have already investigated, we already know how to model the red part, we have to try to understand how to model the blue one. So let's go ahead on this. We can write a few equations. We can write an equilibrium equation. If you consider a segmental element here, the Z of the fiber, you have a sigma F on the negative phase, sigma F plus its variation on the positive one. And these are the equilibrium equation, because this sigma is in equilibrium with the interface tau, with the interface shear the interface bond stress tau, which is developed through the Z. So you can write this equation, this differential equation. This is the indefinite equilibrium equation. Then you have also some compatibility equation, because we are assuming that all displacements happens in this interface. So we consider that the concrete is almost is basically rigid. So we have some axial strain developing in the FRP, which are related to the interface displacement, which is S in this point and S plus the S in this point. So the axial strain by definition is the difference between this displacement divided by the original length of this segmental element. So we have also the compatibility equation, and also we have some stress-strain relationship which deal with the FRP strip, which is always elastic in nature. So you have that sigma on this sigma is elastically connected with the epsilon developed here, the axial strain developed here. And also we have an interface that for the moment is still a linear interface. So we have a linear relationship between tau and the interface lip, as we said here, as we saw here. Okay. So if you put together all this, what you get is a set of differential equation. Basically, you get this equation, which is discovered by the parameter alpha, which is an interaction parameter, whose value is as high as the interface is stiff. As you see here, alpha square is as high as the interface is stiff, or as low as the FRP is stiff. So this is an interaction parameter which governs, which control the shape of the distribution of the interfacial tau throughout this interface. So tau depends on alpha. If you have a very stiff interaction, a very stiff interface, you will have a tau with a very high peak value. If you have a soft interface, you have a tau which is almost uniform. So we'll see some solutions here. So you see here K elastic. If K elastic increases, you have an increase in the peak here. And this is due to to AL, so to this distance between the actual distance, the actual cutoff section and the theoretical support. So as you see here, you can maybe have a more physically based intuition of this phenomenon. If you have a complete strengthening, you have this this quasi-Jurasky solution with some smooth transition depending on the partial interaction. Then, if you have a cutoff section, this part of the bond stress, which is not actually present because there is no interface, is now concentrated here, and this peak is as sharp as alpha is high. So you have for a longer distance, you have a sharper peak, and so on, up to getting a certain tau maximum. So as you see, if we accept the assumption of elastic material, this is the distribution of interface shear, bond shear stresses. Of course, what is clear, what is evident, what is clear in experimental activities, and also what is clear if you know the behavior of materials, especially of concrete, elastic behavior can only be accepted for low stress levels. So it can be probably accepted for serviceability, for service loads, but it cannot be accepted for ultimate ones. So, if you look at before saying that, I forgot to mention that this peak, this peak can be basically characterized by K tau, which is the ratio between tau maximum and the Jurasky value, and this is function of alpha A and alpha A and A to L ratio, so two non-dimensional parameters. But this is true only if and only if we are accepting the linear elastic behavior of interface. As I was saying, the interface is not actually linear, because when a certain level of stress is attained, some cracking phenomena develops the interface just beneath the adhesive layer. So you can probably see that there is a cohesive fracture developing in one of the two adherents. Typically, it develops in concrete. Other kinds of fracture can theoretically develop, even though the cohesive fracture is the most common in FRP strengthened RC beams, and this is a mechanical justification of this. If you zoom this part, you have the adherent, you have the FRP strip, you have the concrete, which is the more brittle component. This is the layer, the adhesive layer. And this, the resulting behavior of this interface is a series. Basically, it results from a series between the elastic behavior of the adhesive, which is it can be accepted as elastic, and the elastic softening behavior of concrete. So if you put these two behavior in series, like it is depicted here, you have probably a tau slip relationship, which is no longer indefinitely elastic, but is elastic up to a certain value of tau, and then you have a softening branch, which can either be modeled as a linear or non-linear, or this is just a qualitative graph. We will see later on that we usually assume that we have a linear softening branch, but there are also solutions based on an exponential, for instance, softening branch. So let's try to understand how the nonlinearity, the cracking phenomena, or the cohesive fracture phenomena, and the nonlinearity of interface affects the behavior of our material glued on concrete. So you have here the same equilibrium equation. We have, if you consider the same segmental member here, element, you have the same equilibrium equation, because equilibrium is equilibrium. It doesn't matter whether you are in the elastic range or the elastic one. Equilibrium is just an equilibrium between emerging normal stresses and interface shear forces, interface bond forces. Compatibility is also compatibility. It doesn't matter whether you are in elastic or inelastic range. This is just a displacement compatibility between. It's just a compatibility equation between displacement and axial strain. What changes is not the stress-strain relationship for the FRP strip, which is indefinitely elastic. The change is just inside the tau slip relationship, which is no longer indefinitely elastic, but is elastic and then softening. So we have a in this writing, it is not an explicit equation, but this writing highlights that tau is just function of slip. It is a general non-linear function of the local slip. So if you put together this, what you have, if you consider that you have an elastic and a linear softening, you can imagine how a pull-out stress, pull-out test happens, you can, for instance, think to apply a force, or better, to impose a certain value of the maximum slip at the end of this. So S1, you get you can solve the equations I reported before. We are in the elastic range, so we have an exponential solution. So these are the tau. I remind you that this curve is as sharp as alpha is high. So if you have a high alpha, which means a stiff interface, you have a very sharp shape, or a very sharp distribution, a very high gradient of this tau. Otherwise, you have a more uniform distribution. If you increase the displacement, but you are still in the elastic range, you still have an exponential distribution, and then this is the maximum value of S3 corresponding to an exponential distribution. Because once you attain S3, any increment of S3 will stress the interface in the nonlinear range. So you will have another distribution of this part. So you will have here the S elastic limit, and this part will be stressed in this. So you have from here to your left, you have displacement which are smaller than S elastic. From here to your right, you have displacement which are up to S4. Here we have S4. And then in this point, the maximum tau is smaller than the tau you attain in this point is smaller than the maximum one. So, and if you proceed with this by imposing higher and higher displacement, you get a certain moment in which the maximum displacement here is just equal to S6, is equal to SU, which means that you have here attained once again tau equal to 0. Any increase in the interface, in the maximum displacement here, will result in zero increase in tau. This means that we have attained the maximum interface strength, the maximum strength in terms of forces, and we have also realized the transfer length, which is the value between the maximum of tau and the value at the point in which tau is 0. We can try to evaluate LE, or at least we can try to understand which are the parameters controlling LE, this transfer length, by this the resulting applied force ultimate slip, which show you what is the usual difference between the F maximum and the F elastic, which can be even equal to 10. But now, let's try to understand which are the parameters actually controlling LE, and we can do it by going back to our equations and modifying it in this way. If you remember the previous slides, you had here Ks, but this was true only in the elastic range. Now we have to write tau as a function of S, generally speaking. If we introduce a very simplified shape of tau, so if we, for instance, if we imagine just for a while that tau, the relationship between tau and S is just like a constant value of tau up to a maximum SU. No? If you have, for instance, you mobilize for an infinitesimal value of S, you mobilize tau R, and then you have this constant value up to failure. So you have a constant value. This equation is very easy to be solved because this is a constant coefficient second order differential equation, whose solution is this one. And if you apply the condition here that the displacement at L equal to LE is equal to SU, as you have here, the displacement here at L equal to at Z equal to LE is equal to SU, what you get is an expression for LE. LE is the transfer length. How much is the length between the point in which tau reduces to 0 and the bonding starts developing, and the maximum tau. So this is the LE. As you can see here, you see which are the parameters controlling this LE. So LE is as long as the strip is axially stiff. So if you have a very stiff strip, you have LE, which is a very long one. If you have, potentially, if you had an infinitely, if EF, TF would were infinite, you will have an LE infinite, something like that. If you have a very flexible EF, TF, this would reduce to 0. And at the same time, the maximum force can be evaluated this way. You can just multiply LE times BF times TR in this specific case, and you get this equation. It is worth highlighting that these two equations have two different meanings, two different scopes. The maximum, the expression of the maximum force depends, as you see here, depends on GF. GF is the area of the tau slip relationship. So GF is the so-called fracture energy, describing the cohesive fracture process. And it is worth highlighting that this formula is valid, can be applied to any tau S relationships characterized by GF. So, regardless of the fact that you have this rectangular shape, or this triangular one, or the other triangular one, if GF is the same, the maximum moment, the maximum force, the maximum applied force is always this one, according to the theory, the cohesive fracture theory we have developed. On the contrary, LE depends on the actual shape of the tau slip relationship. So the parameters are always the same. You have to expect to find out EF, TF at the numerator, you have to expect a square root, you have to expect something related to the ratio between the maximum shear and the stress and the maximum displacement, but this number depends on the shape. So you have P divided by 2 in the case of a bilinear relationship, or radical 2, as we have found for a constant tau S. So this one is valid for any tau slip shape. This one depends, especially this coefficient theoretically depends on the shape of the tau slip relationship. Here you can see this is a ratio diagram explaining how is the force, or if you want, the corresponding strength of the which can be applied to an FRP strip glued on concrete, divided the maximum one, FD, depending on the bonding length. So if I reduce this bonding length below LE, I have reduction, which can be approximately described this way. If I have a bonding length which is at least LE, I have a constant value of FD, which is derived by F max. So it is this 2 EF GF divided TF. So you have these two situations. A clear border, once you have defined LE, you have a clear border. If the bond length is lower than LE, you have a lower force, F maximum, and a lower strength, the bonding strength, FD, F of the fiber, the bonding. Here, if you have that LB is longer than, equal or longer than LE, you attain this F maximum, which means you attain this debonding failure. So this is the way of describing the bonding phenomenon in a pull-out section, in a pull-out test, which corresponds, basically conceptually, which corresponds to the situation you have here at the end. So if you want to evaluate how much is the strength of this final part of the strip, you have to consider what is the bond length, which is basically the length between the last bending induced crack and the cutoff section. If this is lower than LE or higher than LE, you can evaluate what is the maximum force you can potentially apply here, or what is the corresponding strength you can mobilize in this point. Now we have to approach the intermediate debonding. So it is more or less clear how this end debonding works. We have to evaluate the FD maximum according to this relationship. We have to evaluate the transfer length, LE, and the actual bond length. And you can evaluate how much is the maximum FD which can be applied here. So it's easy. You can evaluate FD, compare with this maximum strength. If the stress is lower than strength, you have no problem with the plate end separation. Otherwise, you have to consider that the plate end can occur, and then you have to take the appropriate countermeasures. But now let's move on this more complicated and more peculiar behavior. How is the behavior, the response of an FRP plate glued to the concrete soffit between these two cracks, or these other two ones, these two crack-induced ones, mainly mainly flexure-induced cracks. So we have to try to understand how is the interaction between this FRP strip glued to this soffit, this RC soffit between these two cracks. Let's try to speculate a little bit on this. Actually, we have our beam. As a matter of principle, we can figure out a possible mechanical explanation for the occurrence of the intermediate debonding, because between these two cracks, depending on the applied load, we can evaluate the delta sigma, the actual increase in axial strength, in axial stresses due to the applied forces, and we have to compare this increase in the axial stresses between this section and the other section. We have to compare this increase with the maximum delta sigma which can be borne between these two sections, which can be supported, which can be accepted for these two sections. Let's try to understand how this phenomenon works. So we have this cracks whose distance is SRM. This is the symbol usually adopted for describing the crack distance. We have a FRP strip which is subjected here to a certain F, sigma F, in this point, an initial value of sigma. And in the other section, we have a sigma which is probably bigger because the moment increases in this way, so up to the midspan. So this sigma is bigger than this one, and the increase is the delta sigma. This delta sigma, of course, mobilizes some interfacial bond strength. Now the problem is to evaluate the maximum resisting delta sigma, which allows us to detect whether the intermediate bonding happens or not. How to handle this problem? The problem is more or less similar to the one we have discussed so far, because we have still a concrete soffit with a concrete substrate with an FRP strip glued on it. We have always this equilibrium equation for a certain segmental element here. The compatibility is the same. The interface is also the same with respect to the plate end situation. We have elastic strip, non-linear elastic softening behavior for our interface. But what changes with respect to the previous problem is that here the boundary conditions are different, because in the previous case we had zero sigma here and a certain value of sigma here, if you remember, no? If you can see here, no? If you look at this problem, here sigma is 0, here sigma is non-zero. We evaluate the distribution of tau under these boundary conditions. In this case, for intermediate debonding, we have two non-zero stresses, and our purpose, our objective is to evaluate how much is the maximum delta sigma resulting in the bonding at the interface, resulting in the fact, for instance, that in this point the maximum slip attains S optimate, which is the maximum interface slip before the bonding occurs. So basically we can put together all these equations. I omitted all the mathematical details. Of course, if anybody is interested about that, we can discuss later on the coming days about which are the mathematical details of this problem. But we have a differential problem with some boundary conditions. For instance, here I wrote these conditions explicitly in terms of sigma. If you solve this problem, you can obtain the value of the slips across these interfaces, depending on z, the position, and depending on the initial value of sigma and the final value of sigma, or in other words, depending on the increase. Of course, also the actual distance between cracks is an important parameter, and it goes without saying that the problem is also governed by the fracture energy of the interface and by some key parameters of the glued member. But if you can somehow, usually this is not possible in an analytic way, but you can do it numerically. If you can write this equation, you can also solve. You can also evaluate the maximum sigma, because the maximum delta sigma is the value of delta sigma for which S evaluated at the end of this, evaluated for Z equal to SRM is equal to SU. So you evaluate the maximum delta sigma resulting in attaining here SU ultimate depending on your solution. So if you have all the value of S, you evaluate S at the end of this segment, and you impose here that this value is SU. This is the bonding. This is an incipient debonding condition. And this is the way in which one can evaluate the maximum delta sigma. The problem, as you can see, is rather complicated under the mathematical standpoint. It needs a numerical solution, but we can try to figure out what is the possible relationship between the applied sigma f, so the sigma f we have at the beginning of this segment, and the maximum strength you have on the other side, the maximum delta sigma you have on the other side. The maximum delta sigma, which applied on the other side, results in the bonding for the glued FRP strip. So we can try to understand this. We can try to figure out, based on our physical intuition of the problem. For instance, let's start from the first limit case. Let's suppose that sigma f is equal to the maximum strength for the composite strip. Here, you, for some reasons, have attained the maximum strength of the composite strip. How much would be the delta sigma? Of course, you can have no delta sigma, because any delta sigma, even an infinitesimal one, will result in the tearing, in the rupture, in the axial rupture of the FRP. So this means that if you start with sigma f equal to FFU, the delta sigma is 0. So this is one of the possible points of this mysterious relationship between sigma f and maximum delta sigma. So this is for sure one first point. Let's suppose the other limit case. Let's suppose that sigma f is 0. Well, if sigma f is 0, we go back to the previous problem, the problem of the pull-out situation, configuration. So we know that we can evaluate an FFD, which depends on the properties of the interface, and the problem it depends also on the bond length. So if SRM is shorter than LE, we will have a reduced FFD. If SRM will be at least equal to LD, we will have this solution. We will have this. I'll show here. We will have this. Depending on the fact that the distance between the cracks is bigger or is longer or shorter than LE, we will have FFD, this one, or a shorter one. But this is something which can be easily evaluated. So basically, the point you have here is the expression I've just shown you. You can easily evaluate it. So if you have 0 sigma f here, the delta sigma is the maximum stress which can be applied and which result in the bonding. This can be the square root of twice GF, EF divided by TF, or a lower value depending on SRM. If SRM is lower than LE, you have to reduce it. Of course, if SRM or if the interface is a very strong one, you should consider that the maximum force you applied here can never be bigger than the maximum force, the maximum strength of the composite. This is the situation. This is the ideal situation. It's not a realistic one, but the ideal situation in which you have a pull-out stress which fails due to axial rupture of the strength. So this is really the maximum possible value you can obtain. Up to if the rupture occurs for lower value, you have the bonding. Here you have potentially not the bonding, but axial rupture. It's an ideal case, but you have to take into account this. Of course, it's easy to understand that if you are for whichever sigma f, the one corresponding to this straight line is the increment in terms of sigma f resulting in having on the other side just FF ultimate. So if you have if you have here sigma f, this is the increment you have on the other side to get FFU. So this straight line can never be overcome. The relationship between the applied the maximum delta sigma and the initial FFU can never be higher than this, because this is the maximum strength of the system, which is represented by the axial rupture of the FRP strip. Usually, if you solve the equation I've shown you, you have a curve starting from this point and going up to a certain point whose position is unknown, actually. And this one is the rupture due to the bonding. This branch of this relationship corresponds to the bonding, and then this part here corresponds to the shear to the axial rupture of the FRP strip. So this is how a general relationship between sigma f, the initial value, and the maximum value you can apply before obtaining before the occurrence of intermediate crack-induced debonding occurs. As I said, this is just a qualitative representation. An exact analytical representation of this is not easy to obtain, but there are some solutions which are available in the literature. So basically, how this is, for instance, a possible formulation due to Niedermeyer proposed in the bulletin 2001, in which you find the coordinates in this chart. You find the coordinates of the maximum of 0.1, of 0.2, and 0.3, or the way of defining these three branches. But what is important is that you have a major branch in which the bonding occur, and then a very small one in which you have axial rupture of the bonding. Of course, as you see, the value of the distance of cracks is a very critical parameter which should be evaluated. In the literature, you find some relationships for evaluating this, taking into account both the external reinforcement and the internal one. As you know, for instance, from model code, the higher is the amount of internal reinforcement, the closer are the cracks. Actually, in my opinion, one should consider the crack of the unreinforced member before of the application of the FRP strip, because when you reinforce your member, usually the member is already cracked, so cracks are already formed. So it doesn't make sense, in my opinion, to take into account also the contribution of FRP. So you should evaluate cracks depending on the situation before strengthening. So a possible procedure to check whether intermediate debonding occurs or not should be based on evaluating the actual increase in stresses between two close two close cracks after having established the distance between these cracks. So you know, or you can estimate, you can evaluate how is the distance between cracks. You can then evaluate the delta sigma, the increase. For each crack, you can evaluate the increase in delta sigma between the two sides of the cracks. And then you can compare this strength, this demand, if you want, with the corresponding resistance. With this stress, this demand, with the corresponding resistance, with this capacity, which is here. So, if the stress remains lower than the strength, you have no intermediate debonding. Otherwise, intermediate debonding occur. So the problem now, since the maximum delta sigma depends on the initial value of sigma, and delta sigma also depends on the two sigma you have at the two ends of the crack, the problem now is how to evaluate the sigma, how to evaluate sigma at both ends of the crack. Of course, this can be done via some sectional analysis. This is something already known for RC sections. For instance, if you want to evaluate what is the stress state of materials before strengthening, you have to consider all the loads applied before strengthening. So self-weight for sure, some sustained loads if they are present before or during the application of the FRP strip, and then you can, for instance, assume a linear cracked situation for your maximum for your section, and then you can evaluate the position of the neutral axis in bending as usual by finding out the zero value of the static moment of the resisting section, and then you can evaluate the moment of inertia and evaluate according to the Navier formula the sigma sheet zero and the corresponding epsilon at the top and of course and at the bottom, because this is important. Epsilon zero is an important parameter because this is the epsilon which is developed in the bottom chord of the section when you apply your FRP strip. So the FRP strip, when you apply the strip has no axial strength, no axial strain, inside, but the soft to which it is applied is already characterized by this epsilon zero. So you have to take into account this. So now to evaluate the sigma in a certain section, so we are, for instance, interested to evaluate the sigma in this section, for instance, sigma f in the fiber in this section. How can we do? Well, we have evaluated the initial state of stress before strengthening. Then, after strengthening, we can write two equilibrium equations. Equilibrium equation of forces and momentum, you see, and rotation. You see here, this is the resulting force for the compressed concrete. This is the resulting force for steel, depending in which sigma depend on S. It can be in the elastic field or in the post-elastic plastic field. This is the behavior of the contribution of fibers, because fiber has this axial strain. Fibers are always stiff, are always elastic, This means that its stress is always given by the axial stiffness times the effective axial strain, which is the axial strain potentially deriving by the conservation of plane section minus epsilon zero, which is present at the bottom chord of the section, and then it should be subtracted, as you can see here, because the epsilon in F is lower than the one which should have be attained in the case of plane section remaining plane. This is the equation of equilibrium to forces in the direction of the axis. This is the equation of equilibrium in terms of moments around the neutral axis. So the neutral axis is at the position x from the top chord, and then these equations are based on two main unknown: the maximum epsilon, which controls all deformations, and the position x, which also controls the deformation. So you have two equations in two unknown. You can solve it depending on the external moment, the total external moment. You can evaluate how much is epsilon x maximum, and then you can evaluate epsilon f, and from epsilon f you can evaluate sigma n. So this is the way, the more rigorous and the most straightforward way to evaluate sigma f in a certain section. But it implies the solving nonlinear equations, because these are nonlinear integral equations. So what we can do to evaluate sigma f is to have a stepwise quasi-linear analysis. So we can have, for instance, a first analysis before strengthening, as we said. Then we can consider that we have the strengthened section, on which we can apply a certain increase, a certain moment increment, and this will stress not only the reinforced concrete part, but also the external strengthening. So we have to evaluate a modified position of the neutral axis, taking into account also the contribution of the external reinforcement, a modified centroidal moment of inertia, which is IIFC. SF means that we are considering both the internal reinforcement, the external one, and then the resulting increase in sigma depends on the increase in external moments. And once we have evaluated the increase in sigma in the concrete and on the top chord, we can also evaluate the increase in terms of epsilon in the same chord, and also the increase at this level and also at this level. This epsilon FSF is the increase which depends on epsilon, and this means that it depends on the increase in m, at the fiber level. So this is the epsilon f. And okay, this solution works up to the yielding of the internal strengthening, the internal reinforcement. But the yielding of the internal reinforcement is obtained when the initial strain of the internal bars plus the one developed by means of the moment increment are equal to epsilon sy. If you solve this equation, you obtain, by introducing epsilon, this delta epsilon with the moment, with this moment explicitly inside it, you obtain the moment increment resulting in the internal, in the yielding the internal steel reinforcement, which means that for further increase you will have another section with no contribution, which will have no contribution from the steel reinforcement, which is actually yielded, so it cannot contribute to further delta f, the delta m. That's why delta m is indicated here as delta m f, because it only increases the delta sigma in the fibers, not in the strip, not in the internal part. It can be evaluated with the same technique. You can evaluate a new position for the neutral axis, which only applies for the increase of the moment after the yielding of the internal reinforcement, and this means that you can evaluate also your internal moment and the increment in terms of delta sigma. And this is how this delta sigma look like. Let's suppose that at each point you have a position of one crack. Here we compare the simplified solution based on the pseudoelastic solution, the one I've just shown you here, with a solution based on solving this nonlinear equation I've firstly shown here. So as you can see, the prevision of sigma throughout the strip is quite accurate. So as you can see here, if you want to check whether the interface whether the bonding occurs between these two cracks, we have to evaluate this sigma. We know this sigma. This is the other sigma, so we know the delta sigma, the stressing delta sigma, and then we have to evaluate also the maximum delta sigma available, the maximum strength in terms of delta sigma, and this can be evaluated by just as a function of delta sigma. As you see here, delta sigma in terms of stresses is really, increased after yielding. So, as you see from this graph, delta sigma in the external strengthening is really boosted, is really stronger, or as you can see, more rapid after the occurrence of yielding of the internal form, because after yielding, the only external reinforcement is the FRP strip. So for any increase on the moment, you have an increase in the fiber. So here, for instance, you see that the delta sigma is much bigger in the yielded part than in the non-yielded part, even though theoretically the moment gradient would be bigger here than here. So this is the delta sigma in terms of stresses. You have the delta sigma in terms of strength, which will be evaluated according to the previously described models. And this is, the result of some numerical analysis we presented some years ago, in which the intermediate bonding is clearly connected to the yielding phenomenon. You see, this is the moment in which this is the distribution of stresses inside the bar. So the bar attains its yielding stress, and then it keeps constant. And from this point in which the bar is yielded, the gradient of the stresses developed in the FRP is much faster, is much bigger than below. So interface, the bonding occurs after yielding. So this is the key conceptual difference between the end bonding, which is basically something related to the property of the interface between FRP and concrete, and the intermediate crack-induced debonding, which results from the interaction between the actual strength of the FRP and the demanded stresses, which are strictly connected with the yielding of the internal bar. So when the internal bar is yielded, there is no further help to the no further contribution from the internal bar, and all the increase in the external actions are applied to the FRP strip. So, as you see, I've tried to justify under the mechanical standpoint the occurrence of both the end debonding, which is quite straightforward, and also the intermediate crack-induced debonding, which is a little bit more complicated, as you see, because one have to decide what is the actual distance between cracks. So one have to decide to evaluate the sigma, the axial stresses in all sections, and then to evaluate the stress in terms of delta sigma and the corresponding strength, and compare delta sigma with the maximum delta sigma to assess whether the bonding occurs or not. So it's a quite maybe not complicated, but certainly cumbersome, certainly complex procedure. So this is not usually the procedure which is suggested by codes of standard for taking into account of the possible intermediate crack-induced debonding. Even though this is clearly, at least in my opinion, it is clearly the most mechanically consistent explanation and the most mechanically consistent model. Usually, what guidelines and codes do, they just provide designers with a maximum epsilon, generally lower than the ultimate epsilon of the FRP strip. So the maximum epsilon resulting in intermediate crack-induced debonding. So this is basically an empirical calibration. Somebody took some experimental results from literature and realized that there is a certain correlation between the epsilon, the maximum mobilized epsilon, the maximum mobilized axial stress at the intermediate debonding, and basically the axial stiffness of the glued strip divided by the fracture energy of the interface. And then this kind of formulae were proposed, both ACI 440 or other codes. Also, this formula is actually taken from the Italian guideline, but several formulae proposed by both codes and also by some authors just accept this simplified, I would say also simplistic assumption that the maximum that intermediate crack-induced debonding can be just controlled by controlling the maximum axial strain in the FRP. So if we introduce a maximum axial strain in FRP, we just go back to the sectional problem, because there is another ultimate state. So the section can be at the ultimate state either because the top, the most compressed part of concrete is attains epsilon C ultimate, the ultimate axial strain of concrete, or because the FRP attains its ultimate strain, which is not generally due to the fiber rupture, but is due to the bonding, according to this model, these simplified models. Usually, now we have entered this one of the final section of my presentation, because we are talking about how to evaluate, also in terms of code provisions, the bending capacity of sections, and of course this is framed in a limit state approach. So in any case, we have an effect induced by a design value of the effect, which should be lower than a design value of the corresponding strength. So this is the general assumption. For FRP, we can evaluate the design values of properties just starting from the characteristic value, modifying it depending on some factor which depends on the nature of the material, on the working condition, on the kind of phenomenon we are talking about. So if, for instance, if you want to evaluate the bonding strength, we have to consider this eta, which is higher, because so eta and gamma is the safety factor, which said is higher because we have to be safer with respect to the bonding, which is an uncertain phenomenon. These are some formulation provided by CNR. As you see, you can easily recognize here the formulation for the design value of the transfer length, which resembles the one I've shown you in my presentation. This is the formulation of FBD, which is also similar. Here, this is the maximum force, the design value of the maximum force, which can be transferred in the bond in a pull-out test, which means the maximum force which can be transferred at the end anchorage in our debonding. And this is the formula provided for intermediate crack-induced debonding. So you can evaluate this force, this strength, or the corresponding strain here, just by considering the axial stress, the axial stiffness of the material, and properties of the interface. FC has something to do with the FC is the competence factor, which means since we generally apply this strengthening to existing structures, the FC depends on the knowledge you have on the structure. So on how many non-destructive and destructive tests you have done on your member to evaluate the average compressive and tensile strength. So FC can be either 1.2 and 1.35. This is the Italian guideline, depending on the fact that you have done you implemented a more accurate or less invasive testing campaign. So, as I said, now we have a new limit state, depending on the fact that our FRP develops a certain value of epsilon ft, which is the minimum between the theoretical ultimate strain due to resulting in the rupture of the fiber, which generally is higher than the corresponding value due to intermediate debonding that I've just mentioned before. Of course, just if you consider just a simple geometrical relationship and to take into account that there is an initial state of stress resulting in epsilon 0 at the bottom of this section due to the loads applied on the unreinforced strain, you can evaluate, depending on epsilon f and depending on the possible position of the neutral axis, you can evaluate how much is the maximum epsilon in concrete and how are the epsilon developed in the various levels of internal reinforcement. So this is something which slightly modify the various resulting. This is the resulting force in the FRP. This is the resulting force, if you assume, for instance, the stress block approximation in concrete. These are the stresses in the steel, and then you can evaluate the position of the neutral axis by imposing the equilibrium, and then the resulting moment, the design value of the moment. Here, of course, there should be a bar on each x, which is the solution of the problems. Once you evaluate MRD, depending on the taking into account of the reinforcement, you have to compare this MRD with MED and check whether MED is smaller or bigger than MRD. If the former is the case, you have that no crisis occurs at the ultimate limit state. It should be highlighted that MRD takes directly into account the possibility to have a intermediate debonding crisis, because MRD is evaluated just taking into account that the maximum epsilon is lower than the epsilon FD, which is this one. Okay. So there are also some limit states, some serviceability limit state that should be checked. So when you talk about serviceability limit state, you talk about lower loads. If you have lower loads, you can recover the models we have developed for linear systems. So we have basically we can evaluate how much is the tau at the interface, taking into account the parameters we have shown before, based on the stiffness of the adhesive layer and the distance between the cutoff section and the theoretical support point. We can approximately take into account of the fact that we have not only interfacial shear stress, but we have also some so-called peeling stresses, some interface normal stresses, and then we can evaluate a modified KID to evaluate the stress, the resulting stress, taking into account of the Jurasky one. So this is KID is basically an amplification factor, which multiplies the Jurasky values to take into account of the cutoff section and the stiffness of the interface. Now, I had no. Somebody just quit the presentation and said goodbye to everybody. I'm almost completed this presentation. I would only like to show you a work example, which is based on a real application. Maybe it's not really the application which was done, but it's at least a realistic application. We are in our bio campus in the University of Salerno. This is a small campus in which it was recently established at the Faculty of Medicine. It was recently established there. This campus was recently strengthened. These are some pictures of the strengthening. In shear, you see these inclined FRP strips, which be linked to shear strengthening, which will be covered in the next presentation. But here they did also some flexural stiffness, flexural reinforcement, because they found also some cracking, some bending induced cracking. These are orthogonal cracks, so these are clearly bending induced cracks. We have very long beams spanning for around 10 meters, which are probably under-designed, because these were designed in the 70s, and now maybe they experience some increase in loads, and they are probably under-designed for the current needs. So they exhibited some cracks, and they were, since the designers were concerned about these cracks, they have designed a possible strengthening. They did it with steel. Now we figure out how an FRP based strengthening would have looked like. So we have this data. We focus on this intermediate span. The span, as I said, is around 10 meters. These are the section properties. So D is 40, 90, the concrete cover is 4 centimeters. These are the information about the area in terms of internal strengthening. At the internal support, of course, you have bigger strengthening, bigger reinforcement on the top side, because we have tendentially negative moments, and in the mid-span you have bigger strengthening in between, below the lower part. We know something about materials, because we know that we assume at least that materials are based on an average value of concrete cylindrical compressive strength of 20 megapascal, which is a lower strength, but this is an existing structure. We assume a confidence factor of 1.35, because we're supposed to have that we have done a few in situ tests. We know also the average value of the reinforcing steel, and these are the loads we assume for our beam, divided in self-weight, permanent loads, and variable loads. Now we do an analysis. So the analysis, these are the loads at the ultimate limit state. We usually assume a magnification factor of 1.3 for permanent loads and 1.5 for variable loads, according to the Italian standard, and also according to the Eurocode standard. We have also a service load condition, which is just the summation. 458 is just the sum of these three nominal values. When we carry out an elastic analysis, we have that a minimum value of negative moment, which is 689 kilonewton meters, and a positive one of 344 kilonewton meter. As you know, we can do something, what we'll do later. We can evaluate the capacity of the S-built configuration. The S-built configuration is characterized by a capacity of 655 kilonewton meter and 328 kilonewton meter. So we have that both sections, both here on the intermediate support and in the midspan, are under-designed, because this is bigger than this and this is bigger than this. Of course, we can only strengthen in the bottom of our section, or at least it is more practical to strengthen only at the bottom. So we can do something which is allowed by Eurocode, for instance. We can redistribute the elastic stresses, so we can assume that the negative moment is just equal to the corresponding resistance, and then we can just increase by equilibrium the positive one. So the positive one passes from 344 to 378. This means that, as you see here, since the strength in positive moment is 328, we have a deficit in this strength. We have to strengthen our section to bring its stiffness, its resistance from 344 to 378 at least. So how can we do it? Well, we can consider a composite system made of these strips. These are the properties. We consider to install just two layers, two plies of FRP. We consider these parameters, which are related to some safety factors, which are provided by our regulation. And then, according to our calculation, we can calculate the interface, the design value of the fracture energy and the corresponding, you see here, this is the corresponding effective axial strain resulting in intermediate debonding. So as you see here, this is 3 per mil, 0.3%, which is 5 times lower than the actual the ultimate strain resulting in the rupture of FRP. So actually, due to the intermediate debonding, we have to reduce significantly the effectiveness of this external strengthening. So we have to work with this. And we can evaluate our initial state. We suppose that we have only the sustained loads, so the self-weight and the permanent load. This result in this moment, and this is the epsilon zero. This is the strain developed at the bottom chord of the concrete section due to the initial loads. With this value of the initial strain, we can evaluate our the strength of our section according to the theory we have developed so far. So, for instance, we can evaluate the position of the neutral axis, which is at the end we will find 95. Why it is 95? Because we have a contribution of concrete which is evaluated according to the conventional stress block contribution. So it is the strength of the concrete times the width of the section times 0.8 times XU you have here. Then this is the contribution of the internal moment, of the internal strengthening, the internal ribbers. So you have the top ribber, the small one, no? This is the small area, resulting in this contribution, in compression. The bottom one with this neutral axis, this is the tensile strain, and this is the corresponding strength. This is the resulting force in the steel ribbers, top and bottom steel ribbers. These are also the epsilon Fy. How we have evaluated this? We evaluated this by internal compatibility and then by subtracting epsilon zero. You know? So we have evaluated the epsilon Fy by considering the maximum epsilon u minus doing the equivalence, the similitude in this triangle, and then by subtracting epsilon u. Once you evaluate this, we have multiplied it by the Young modulus and then by the area. We have obtained this and u. If you sum this plus this plus this, you get 0. Of course, this was a solution obtained via a numerical procedure which can easily be implemented in Excel. So once we have known XU, this is sufficiently high to confirm that the ultimate limit state is attained because the maximum, the top chord of the bottom, the FRP is the ultimate limit state. Then we have the contribution of concrete, of steel, and of fiber. This is a mistake here. This is fiber. So you have the contribution of concrete, the contribution of steel, the contribution of fibers. And this is 385.95, which is enough to cover the resulting moment, which was, if you remember, 378. We have 385. So the most stressed section, this one, is okay. Is checked in terms of bending moment, including the possible effect of intermediate debonding. Now we have to make sure that we have no debonding at the end. Of course, we can evaluate the transfer length. We can provide, we can evaluate the position of the last crack, because we know the cracking moment, so we can evaluate depending on the external load what is the position of the last crack. Then we can provide this strengthening with just this length, and we are sure that the stressing, the stress in the FRP strip is far below its maximum strength. So we have evaluated we have avoided here the end debonding, but we have also taken into account the service load. So we have a certain distance A from here to here, and this will result in a certain value of KID and a certain value of tau evaluated for the service loads. And this tau is bigger, is higher than the one allowed by the code. So this means that we have a stiffer, we have a too stiff interface, but we cannot change it. But what we have a bigger value of, a too big value of A, of the distance between the cutoff section and the theoretical support. So what we can do, we can try to just extend the anchorage to reduce E. What we've done, we just extend from 224 from the support. So we put just 10 centimeters more. So we put to 125 to 115, and then we reduce significantly our maximum stress. And this is how to meet both limit state, serviceability limit state, and ultimate limit state. Few words to say something about alternative solutions, because as you saw, FRP, externally glued FRP, is characterized by this detrimental, this problem with the bonding. With the bonding, and it only works for variable loads. It has no effect on permanent loads. Of course, if you want to have a contribution of external FRP for permanent loads, you have to, for instance, one of the solutions is to pre-stress this FRP. And this is not, of course, covered by this presentation, but these are some slides which show you how a pre-stressed solution is less effective than a pre-stressed solution is more effective than a non-pre-stressed one. And also, you have also other solutions which try to improve the interaction between FRP and concrete. These are based on near surface mounted FRP, which are aimed at increasing the specific surface of the interface, which are quite used also for masonry. And more recently, it was developed also some mechanically fastened solutions, based on FRP, even though these strips are not common strips, but these are bearing enhanced FRP strips, which means that they are not uniaxial, simply uniaxial strips, but they are reinforced around the holes which are needed to nail or to bolt the strip to the RC member. These are some results of this about this technology. So conclusions are summarized here. We said that probably the need for strengthening of existing structures are going to be more and more common because of the aging of the existing structures, because of the increase in load and service loads, because of the increase in safety standards of provided by codes. So this means that our structures will be more and more in need for strengthening. FRP are certainly more and more common. Certainly a technically feasible solution for this problem. Of course, there are some open problem, and designers should be quite careful in designing interventions, taking into account of the bonding failure, which are really peculiar failure modes for our systems, and some alternative solutions are being developed or are developed for trying to reducing this problem. These are probably these mechanically fastened solutions or other alternative solutions I've shown at the end of my presentation. So I hope that this presentation would have been of your interest. I hope that everything was clear. If this is not the case, I kindly ask you, and I warmly invite you to answer questions, to have possible clarification about any unclear aspects. So, do you have any question? Is there any question from the audience? No questions?
Thank you, Enzo, for this nice presentation.
Excuse me? Can you repeat, please?
Thank you very much, Enzo, for this nice presentation. It's Emmanuel speaking.
Okay, great. Thank you, Emmanuel. Thank you, Emmanuel. Thank you for organizing this cycle of seminars, and also for hosting me for this webinar. So, if there is no question, if no request for clarification, I thank you once again for your attention and for joining this presentation, and I kindly invite you to quit the classroom so that I can shut down the platform, and because the platform should record this presentation, which will be available soon to be watched offline. So please, if you can quit the classroom, and goodbye to the next webinar. Hello?
Don Jose?